Welcome to Forces, Gravity. There are 4 fundamental forces that govern the universe. Have you ever wondered why the nucleus of an atom stays together with all those positively charged protons that repel each other? The strong nuclear force is responsible for holding the nuclei of atoms together. It is by far the strongest force, but only acts over short ranges of order, 10 to the negative 15 meters. So this is not a gravity force. We're just talking about the 4 fundamental forces that govern the universe. So that's one of them. Another one is the electromagnetic force, is the second strongest force. It causes electric and magnetic effects, such as the repulsion between like electrically charged particles. So if you have like 2 positive charged particles or 2 negative, it repels each other. Okay? And the interaction of magnets. It is long-ranged and can be attractive or repulsive and acts only between pieces of matter carrying electric charge. So these obviously repel each other because they're like charges, but if they were opposite charges, then they would be attracted to each other. A third force is the weak nuclear force is responsible for radioactive decay and neutrino interactions. It has a very short range, and its name indicates it is very weak. So these are three of the 4 forces that govern the universe. We're not going into these in detail, and we're going to be focusing on gravity, which is the 4th one. By far the weakest, the gravitational force is by far the weakest force, but very long-ranged. Furthermore, it is always attractive and acts between any 2 pieces of matter in the universe. These 4 fundamental forces determine the structure of the universe. If the strength of any of these forces changed, the universe would change dramatically. All 4 forces are very interesting, but since we're focusing on Newtonian mechanics, as opposed to quantum mechanics, let's focus on the gravitational force. Recall the story of Newton and the apple. What caused the apple to fall on his head? What causes the moon to revolve around the earth, and the earth around the sun? The answer is the force of gravity. Gravity is an attractive force, meaning that the force always pulls objects closer rather than pushing them away. Also, gravity is an at a distance force. That is, the apple didn't need to be touching the earth to experience its pull. Did you know that everything that has mass has a gravitational field? That means that everything with mass, the earth, the sun, an apple, you, and even an electron, is attracted to everything else with mass, anything else that has a mass. Have a look at the person next to you. Did you know that you are attracted to that person, gravitationally at least? Keep in mind that we keep referring to mass. Mass and weight are 2 different properties. Mass is how much matter is in an object, like how many cells, how much stuff is in something. Weight is related to gravity. So if I have the same amount of matter whether I'm on Earth or on the moon, but my weight changes due to the gravitational pull of the moon versus the Earth. So when we refer to mass, we're talking about how much matter something has. In fact, this is how our sun and planets and satellites were created. Bits of cosmic dust attract each other and combine to create larger cosmic dust bunnies, which attract even more cosmic dust, eventually creating stars, planets, and moons. Here's a thought experiment. Imagine that you and your beloved are the only 2 things left in the universe, billions of kilometers apart. Would the 2 of you ever meet? What if you both had a velocity that was sending you away from each other? So, if you were the only 2 things in the universe, right? So there's no Earth, nothing else, right? So either way, the gravitational force would reunite you. It would just take a really long time. On Earth, we know that the acceleration due to gravity is about 9.8 meters per second squared down, and we use the symbol lowercase g to symbolize acceleration of gravity. Using Newton's second law, we see that the force of gravity on an object must be, so like here, if we look at Newton's second law, F equals ma, and we know that acceleration due to gravity is g, so if we're talking about, if we're doing an equation where gravity is the thing that's causing, is the force that's on an object or whatever, then we would place that 9.8 meters per second squared in for acceleration. If gravity is the only force acting on the object, then we would have force of gravity is equal to mass times g. We use this relationship when we are dealing with objects on or near the surface of the Earth. The force of gravity acting on an object is more colloquially called the object's weight. Physicists distinguishing mass, which is the amount of matter an object has and is measured in kilograms, with the weight, which is a force and is measured in newtons or pounds. Also, mass, in the English units, you have pounds mass, and pounds force. And it just so happens that these are typically on Earth equivalent. So that is a little bit more confusing than using the SI method, which is using different units like kilograms and newtons for mass and weight. If you were to travel to a different planet, one with a different acceleration due to gravity, your mass would remain the same, but your weight would change depending on the characteristics of that planet. So for example, on Earth, I said that I weigh approximately 600 newtons. And that's because the Earth is very massive, and so it pulls down with me with a lot of force. However, if I was on the moon, the gravitational pull of the moon is approximately 1/6 that of the Earth. So on the moon, I would only weigh 100 newtons. So even though I have a mass of 60 kilograms on both the Earth and the moon, my weight would change drastically. Example, a 150-gram apple experiences gravity and falls towards the Earth. Determine the force of gravity acting on the apple. Okay, so we have our equation, F equals ma, right? But here we're talking about force of gravity, so our F is sub g. Our mass was 150 grams. And we need to use, when we're using this equation, we need to use, our units are going to be newtons, kilograms, and meters per second squared. We can't put grams in here. So we need to convert our 150 grams to kilograms. And if you remember, King Henry died by drinking chocolate milk. Okay, so we are at grams, which is our base unit, and we want to go to kilograms. So we have 150. We're going to move our decimal place over 1, 2, 3, 1, 2, 3, and we get 0.15 kilograms. And our acceleration happens to be of gravity, 9.8 meters per second squared. So if we plug this in, F sub g equals mg. F sub g equals 0.15 kilograms times 9.8 meters per second squared. Now keep in mind that our g, see here we have g is down, and so we can change that just to a negative, okay? So our force of gravity, when you multiply this out, is negative 1.47 newtons. So that means that the apple is being pulled downward with a force of 1.47. Or you could say that the weight of the apple is basically 1.5 newtons. When an object is in free fall, it does not necessarily accelerate towards the ground for its entire trip. If air resistance is large enough, the downward force of gravity will balance with the upward force of air resistance. So as you, like, if you had a parachute, if you're like falling and you have a parachute, right? You're not going to be accelerating at 9.8 meters per second squared all the way down, because you have the force of gravity pulling you down, but you also have the force of air resistance pulling you up. When this happens, the object no longer accelerates toward the ground. Instead, it moves at a constant velocity called the terminal velocity. Okay, so let's look back here for a second, because this can be a little bit confusing. So if we have an object that, let's say a ball, or let's just say we have something that we drop it, like, and at time 0, as soon as it's let go, out of a plane or whatever, it's instantaneous. Like at that second, it was moving. Actually, let's rephrase this a little bit. Let's say that you're at a really, 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 really tall cliff, and you have a hand and it's holding onto a ball, and it lets go of that ball. Okay, and so here we have time 0. At time 0, the speed of the ball is going to be 0 meters per second. But the acceleration of that ball is going to be 9.8 meters per second squared down, right? And what force do we have on this ball? We have the force of gravity, right? But you also have air resistance. But right now, because if you stick your hand out the window when you're driving in a car, and you're not moving, there's no air resistance at that point. So really the air resistance, the force of the air resistance, is nothing at this moment in time. But then a second later, now the ball's here. This is time equals 1. Okay, 1 second. At this time, now it's speeding up. So now it's moving approximately 9.8 meters per second squared, we'll say, maybe a little bit less. But as you stick your hand out the window, right? So now you're starting to feel the wind because you're moving, right? And so you're starting to get some air resistance. So now you have the force of gravity, right? But now you have a little bit of air resistance. So you have an air resistance moving up. So now your acceleration, or your forces on this object, you have 2 forces, right? And then at time equals to 2 seconds, now you're going a little bit faster, right? And so now, as you get faster and faster, and when you stick your hand out the window, as you get faster and faster, that air resistance builds up, right? And so as the ball goes faster and faster, it's going to keep going, so that eventually the force of the air resistance is going to be equivalent to the force of gravity. And when that happens, you don't come to a stop. Remember, you're going really, really fast. It's just you went from going super duper, from accelerating. Every time this air resistance force increases, your acceleration decreases, but you're still going fast. So here you're going 9.8 meters per second. And then I'm just estimating here. At this point, you might be going closer to 15 meters per second for velocity. And then here you might be going, when it reaches terminal velocity, maybe you're going, 20 meters per second or something like that. And that's the fastest you're going to go. Now you're going to keep going that speed. The ball's going to keep going at that speed, because now the net force on this ball is 0, because you have the force of gravity equals the force of the air. The net forces is 0. And so it's going to continue at a constant speed in that direction until a different force, or until the forces change. I know that's a little bit confusing, but just wanted to kind of go through that. So let's go over this. When this happens, the object no longer accelerates towards the ground when the air resistance is equivalent to the force of gravity. It's not accelerating. It's still going really fast, but it's not accelerating. Instead, it moves at a constant velocity called the terminal velocity. The terminal velocity of an object depends on many factors, including the object's mass and the surface area and the density of the air. So for example, if you have two objects, let's say you have a brick that's falling, it's thrown out of an airplane or whatever, and then you have, or actually, let's use a different example. Let's say that you have a skydiver that's in this position, and he has his parachute on. You have a skydiver in this position, he's got his parachute on, and then you have a skydiver with the parachute open. Okay, the mass in all three of these is the same, right? But which one is going to be able to achieve the greatest speed? It's going to be this one, because they have the least surface area. So the surface area is a big determining as to how fast something goes. The density of the air would make a difference. If you have thicker air, like if you go up to the top of Mount Everest, the air is thinner. And then the object's mass. So if you have, so those are the three factors that are used to determine the maximum terminal velocity something can reach. Okay, let's do some examples. Draw the free body diagram, then find the acceleration of a 65 kilogram skydiver who jumps out of a plane and experiences 115 newtons of air resistance. B, achieves terminal velocity. Okay, so here we have our skydiver. Mass is 65 kilograms. We have the air resistance as 115 newtons. And it wants to know, and here we can find out the force of gravity is this, right? So we plug in our mass, which is 65 kilograms, and our acceleration due to gravity, which is 9.8 meters per second squared. And we get the force of gravity is 637 newtons. So what is the net force? This means sum. So when I want to find the net force, I can sum up the forces in the x direction and the y direction. So what is the net force on our skydiver, right? We have 115 newtons. Excuse me. We have 115 newtons, and this is going up, right? And we have 637 newtons, and this is going down, right? So we can say that this one's negative, and we can add those up. Okay, and so when we do that, we find that 115 minus 637, we get 522, negative 522 newtons, okay? And so then we have F equals ma. The question was, oh, we're just supposed to find, yeah, it says find the acceleration, okay. So here we have negative 522 is equal to, and that's newtons, that's equal to mass, which is 65 kilograms, times acceleration. So if we plug this into our calculator, we could find the answer to that, which is acceleration is going to be 8.03 meters per second squared down, or approximately 8 meters per second squared down. Okay, and here for the second one, we have our air resistance. Well, on the second one, it says it achieves terminal velocity. So what do we know about when it achieves terminal velocity? We know that the net force has to be 0. So then that means that the air resistance has to equal the force of gravity, which means that this air resistance would be 637, and the force of gravity is 637. So our net force, therefore, is 0, and therefore our acceleration would be 0 here. Any questions?